Hello, my name is Ritvik Sarsani and this is my Lab 5 Magnetic Braking with Faraday's Law. So this is the introduction for this lab. So the purpose of this lab is to record data of a falling bar magnet through a conductive tube of aluminum foil and then to create a computational model of this in order to understand how Faraday's Law works. And so the main physics principle behind this lab is Faraday's Law, which relates to magnetic flux to the Curly electric field along the closed path, and this creates an EMF and current that produces another magnetic field. And so in this lab, the falling bar magnet creates a current in the aluminum tube, which creates a magnetic field that actually affects the bar magnet. So the fundamental principles of this lab is mainly just Faraday's Law. And Faraday's Law is a wire moving through a magnetic field that creates an EMF as explained by this law. And so the observations of the computational model that we had, so we set the tube length, I had a tube length of 0.48 meters, and the inner radius of the tube was 1.635 centimeters, and then the tube thickness was 0.23 centimeters. And then, so the north end of the magnet was facing down as the magnet was dropped, and then the magnetic dipole from the previous lab is 3.13. So these are the results from the observational model. So as you can see, we recorded the duration of the magnet inside the tube in seconds, and we had 5 different trials. So as you can see, the numbers of 5 different trials are stated. And then we averaged all 5 different trials, and the average time was 1.696 seconds. And so moving on to the coding section of the lab. So first we took all those numbers from our computational model and then set it in the starter code. And then after changing the geometry to match my experiment, then we created a function to calculate the magnetic field of the bar magnet as shown, and it was taken mostly from my previous lab. And so moving on, after that we calculated the d flux dt through each ring due to a falling magnet by subtracting the position of the ring from the magnet and using that to calculate df dt with the formula from lecture 43. And then after that, the current in the ring was calculated using Faraday's law. So we did d flux dt divided by the resistance in each ring to find the current. And then after that, the B field at each ring was also calculated using Biot-Savart's law. And that's shown by steps 5 and 6 here. And then moving on to the last parts of the code. So the last parts was to calculate gravitational force and net force. And so we just did that by taking the force of gravitational force and adding it to magnetic force to find the net force. And then we also had to update the magnet's velocity and position before the graph of velocity versus time was calculated as the magnet was dropped. So this is my computational model. As you can see, that as the magnet was dropped, there's 2 different colors. There's a blue and red color, which shows like the different directions of the magnetic current. And then as you can see by the velocity versus time graph, like the velocity does actually even out and become a straight line as time continues. And as we can see, the time in the tube, as shown by our computational model, was 1.724 seconds instead of the observational model, which I got was like about 1.696 seconds. And so interpreting this, so first we interpreted the coloring. So I said the blue current is clockwise and the red current is counterclockwise because the current on top of the magnet is blue, and the current coloring is more intense the closer it is to the magnet. So the red ring represents the increasing current, and then the blue ring represents decreasing. And so if the magnet was flipped, I'd say the dynamics of the system does not change even when the magnet is flipped. And in comparison to the real world time I observed was slightly less than the computational model. The computational model could be more accurate if it could mimic exactly how the magnet would fall with given all the variables are accounted for. And once the magnet is inside the tube, the magnets of the magnetic force and gravitational force are equal. So the magnet has constant velocity inside, which is why the graph straightens out. And in conclusion, we asked what if the resistivity of the conductor was reduced as close to possible to zero, would the dynamics change? And I said if it was as close as possible to zero, the result would be a very highly induced current. and the magnetic force would be much higher than the gravitational force, and the dynamics of the bar magnet would flip instead, and the magnet would probably go upwards instead. And we also asked what if there were holes and slots that were cut into the tube, how would this affect the rings of your current model? And I said, like, if there were holes and things in the tube, the magnet would go, whenever the magnet would go near the hole, there would be no induced current in that ring, so the rings would not be used when calculating the net magnetic force on the magnet. That's it. Thank you.